Our mission today, and we're definitely on board,
Let's do it.
is to unpack the captivating, though still hypothetical, ways in which these DTF concepts, things like time flowing at slightly different rates, a fundamental field often called phi or chi.
Right, that scalar field.
In this idea of quantumness, let's call it Q, might provide a new lens, maybe, through which to view the origin of the Born rule and the crucial role of that squared amplitude in quantum probabilities.
So yeah, get ready to have your perception of reality potentially bent a little.
Exactly.
Okay, so that raises a key question right off the bat, doesn't it? What exactly is differential time flow? What does it mean?
Good point. Let's pin that down. Based on the sources you sent, differential time flow simply means that time might not tick at the same rate everywhere.
Not uniformly.
Especially at a very fundamental level, right? The core idea, which is pretty mind-blowing when you think about it.
It really is
that the speed at which time passes could be slightly different. It's expressed as this factor f, which equals 1 plus a tiny amount.
Epsilon sub q.
Exactly, f1 plus epsilon. And this tiny variation depends on something called local quantumness, or Q.
Okay, so Q is like a measure of how quantum Maya places.
Sort of. Think of it as a measure of how strongly quantum effects are present or dominant in a particular little patch of space-time.
So imagine space-time not as like a perfectly steady clock ticking the same everywhere, but more like a landscape, maybe, where time flows ever so slightly faster or slower depending on the local quantum weather, if you like.
That's a great analogy, the quantum weather. I like that. Precisely. Now, to see how this might connect with the Born rule, we need to just quickly touch on two central mysteries in quantum mechanics.
Okay.
First, the measurement problem. That strange leap from a quantum superposition, where a particle can exist in multiple states at once,
The both-hand state.
to a single definite state, the either, when we measure it. How does that happen?
The collapse of the wave function. Still debated heavily.
Absolutely. And then there's the Born rule itself, this seemingly just imposed rule that tells us the probability of seeing a particular state is proportional to the square of its amplitude.
Modulus squared, technically, but yeah, the square.
Right. Why the squaring? That's the fundamental question we're circling back to.
And the material you shared, the source material, starts to weave a really fascinating speculative connection between these ideas in DTF.
Okay, here's where things get really interesting. The source proposes a hypothetical scenario.
Right.
Where the active measurement itself causes a significant change in this quantumness, this Q value,
Local.
in the area of the system we're actually observing.
Okay, so measuring stirs things up quantum-wise.
Exactly. And this shift in Q, in turn, could dynamically activate that scalar field we mentioned, phi or chi.
The field gets involved.
Think of it like a dimmer switch being turned up, maybe,
Yeah.
bringing this field into greater influence locally.
Okay.
And one of the suggested effects, just one possibility of this activated field, is a phase change in local time. A shift from that slightly varied flow, F1 plus epsilon,
Back towards more standard uniform flow.
back towards F being very close to 1, Fed 1.
So the act of measuring isn't just like passively recording what's already there.
Does it seem like it in this picture?
Instead, it could be actively triggering this dynamic interplay between the quantum nature of the system and this fundamental field, which then has a say in how time itself progresses locally. Wow.
But the speculation doesn't stop there. This is where we really have to, engage our imagination.
Okay, I'm ready.
What if this Ficci field, during this dynamic transition caused by the measurement, is not only responsible for the collapse of the wave function, picking one outcome.
Right, the usual job assigned in some collapse models.
But is also actively interacting with the various amplitudes within that initial superposition, somehow like nudging them, making some more influential and others less so.
Whoa, so the field isn't just a passive stage, it's an active player in the outcome selection.
That's the idea being floated.
It's quite an imaginative leap, isn't it? To consider this Ficci field as a fundamental modifier of space-time at these tiny scales.
It is.
Responding to the underlying, quantum graininess defined by Q.
Exactly. And the source introduces this really captivating thought. What if the larger the magnitude of a specific amplitude in the quantum description,
So the component describing one possible outcome.
the stronger its quantum influence on this local quantumness Q?
So bigger amplitude means more. Quantumness influence locally.
Kind of. It's as if the potential outcomes are subtly vying for dominance over the local conditions of reality itself, even before the measurement is complete.
Okay, this then raises a crucial question, right? Could this interaction then somehow favor the outcomes that initially had the stronger quantum influence?
You're getting it.
Those with the larger squared amplitudes, it's almost like a self-fulfilling prophecy in reverse, where the initial potential strength influences the final outcome's likelihood.
That's the core of the idea. That's exactly it. The thought is that as the Ficci field adjusts during measurement, as Q changes,
the time sort of resets.
This adjustment might dynamically favor states that started with a more powerful initial quantum presence, which mathematically is captured by a larger magnitude square.
Right, the at2 term.
The source even wonders, speculatively of course, if the rate at which local time changes, that's F dot F,
the time derivative of F,
or the energy exchange with the field, could be related in some way to these squared amplitudes.
That's fascinating. A potential dynamic process where measurement mediated by this field in the flow of time isn't neutral observation.
Not at all.
But actively steers the outcome based on the initial quantum state's characteristics, specifically the amplitudes.
It's like the different possibilities are in a race to become the actual outcome. And those with a bigger head start, a larger R2, have a better chance of winning.
A quantum race mediated by space-time itself.
Yeah. The source even considers the possibility that these stronger potential outcomes might, in some sense, occupy space-time more effectively or maybe more quickly during this measurement event.
And the speculation becomes even more intricate, doesn't it? It proposes that quantum fluctuations within this Ficci field,
the field itself is quantum,
might not just be random noise, but could actually carry information about how the probabilities, the amplitudes, are distributed within the quantum superposition.
So picture this. As the field settles down after a measurement,
finds its new state.
This settling isn't just uniform or random. Instead, the source suggests it's guided by the energy or perhaps the emphasis linked to each amplitude.
Okay.
And this energy or emphasis is proportional to the square of that amplitude's magnitude. A2 again.
So if we think about the bigger picture here, the Born rule in the speculative view isn't just some arbitrary rule we impose on quantum systems from the outside.
No, it's not just postulated.
Instead, it kind of emerges as a natural consequence, a characteristic of how space-time itself behaves dynamically during the act of measurement.
Exactly. The Ficci field, reacting to the system's quantumness, Q, which carries this amplitude information, effectively guides the collapse in a way that favors the outcomes that had more initial weight in the quantum mix.
And that weight is mathematically represented by the square of the magnitude.
Precisely.
Now, it's really crucial to emphasize, as the source material does,
yes, let's be clear,
that this is highly speculative. There isn't a fully developed mathematical model within the current understanding of DTF to definitively show how this process would unfold.
No equations proving it yet. It's conceptual.
Right. It's an interpretive framework, a potential direction.
But it's a powerful way to connect these very abstract ideas, isn't it?
It is.
And the source pushes the boundaries even further, asking us to imagine the superposition,
before measurement,
as a particle simultaneously exploring all its possible states, but each with a slightly different flow of time, governed by that local Q.
Which itself is influenced
by the strength of the amplitude associated with that state.
Oh, wow. So the quantum realm is this constant negotiation of possibilities where even the flow of time isn't fixed but responds dynamically to the underlying quantum potential.
That's the picture being painted. And then the Ficci field is envisioned as a kind of, fluid of space-time.
Okay, like a medium.
Yeah, that seeks to settle after this measurement disturbance, this change in Q. And the source introduces this idea of intensity of a potential outcome.
Intensity.
Suggesting that A2, the squared amplitude, actually represents this intensity or maybe energetic emphasis within the superposition.
Okay, so intensity is proportional to A2. How does this fluid of space-time then resolve to a single outcome?
Right. So the source proposes the Ficci field acts as a mediator of choice.
A mediator.
During that transition in time flow we talked about, it interacts with these different intensities.
The intensities of the different possible outcomes.
Exactly. And the idea is that stronger intensities, bigger E2, lead to a more powerful or maybe faster change in the time phase, or perhaps a stronger reaction from the field itself, effectively locking in reality to that particular outcome with a higher intensity.
Okay, so stronger intensity gets chosen more often, essentially. And building on that, the source that quantum fluctuations within the field itself.
The field's own quantum jitters
Might act as a kind of distribution mechanism.
How so?
Well, these fluctuations could perhaps distribute the final reality among the various potential outcomes, with a likelihood or maybe the frequency or magnitude of these fluctuations favoring a particular outcome being proportional to its intensity, S2.
So the field's own quantum nature helps ensure the probabilities line up with the squared amplitudes.
That seems to be the suggestion.
Right.
It's favoring the realization of outcomes with higher intensity.
And the source also touches on how epsilon, that tiny difference in time flow,
The DTF.
and the energy exchange could be quantitative measures of this intensity, or maybe the effort needed to bring about a specific outcome.
Connecting it back to energy.
Yeah, perhaps there's an energy cost or a specific duration of time change linked to the collapse to a particular state. And maybe that cost or duration is proportional to ED2.
Which reinforces that core concept of DTF, doesn't it? That energy and the flow of time are intrinsically connected.
Exactly. Now, a crucial point, and one you rightly highlighted earlier.
Probabilities can't be negative.
Precisely. Probabilities must be non-negative numbers between 0 and 1. How does this framework handle that?
Good question.
The source addresses this by suggesting that the instantaneous energetic contribution of quantum vibrations to the Fichy field.
Okay, an energy contribution.
Which is given by ED2, since energy density often goes like the square of a field amplitude, might be the fundamental driving force behind collapse.
So ED2 represents something inherently positive, like energy density.
Exactly. The field reacts to this non-negative contribution, and the probability of collapse into a state is proportional to this local instantaneous energetic contribution.
Which is ED2.
Right. It's actually quite a neat way to see why a squared quantity, which is always non-negative, naturally leads to non-negative probabilities.
That does offer a compelling possible explanation for why the square of the amplitude is so fundamental. It might directly relate to a physically meaningful and inherently non-negative quantity like energy density or intensity.
Yeah, it could. Yeah. Then the source ventures into even more speculative territory.
Oh, there's more.
Oh, yes. Introducing the intriguing idea of a coupling term in the Lagrangian.
Okay, the Lagrangian, for listeners, that's like the master equation, the fundamental recipe that describes how a physical system evolves over time.
Right, a very high-level description. And this hypothetical term would link the Fichy field with the intensity eddy of the quantum field.
How'd that look, roughly?
Something along the lines of the Lagrangian L, being proportional to negative g, some coupling constant, times phi squared times 2. So Ehlers-Guettu.
Okay, so there's an interaction term connecting the scalar field phi and the quantum field intensity A2 if we think about the broader implications.
Yeah.
That kind of coupling term would fundamentally alter how the Fichy field behaves when quantum matter described by A is present.
Exactly. And the suggestion is that this coupling could create a kind of energy landscape for the Fichy field.
A potential energy landscape.
Yeah, with multiple attractive points or local minima, basins of attraction.
Okay.
And here's the really interesting part. The depth of each of these valleys in the landscape would be proportional to the S2 of the corresponding outcome.
So the more intense the quantum possibility, the bigger S, the deeper the valley in this energy landscape for the Fichy field associated with that outcome.
That's the idea.
Okay, that raises the obvious question.
Yeah.
How does the system then end up in one of these valleys corresponding to the measured outcome?
Well, that's where the quantum nature of the Fichy field itself comes back into play.
The field isn't classical.
Right. The field isn't just a smooth classical entity. It experiences its own quantum fluctuations. It jitters.
Okay.
And this allows it to potentially tunnel or just transition between these different minimas in the energy landscape.
Quantum tunneling for the space-time field itself.
Sort of, or at least quantum transitions. And the likelihood of these transitions would be strongly influenced by the depth of the minima, which relates to ED2, which, as we discussed, is related to ED2. So the deeper the valley, meaning the higher the initial ED,
the more probable it is for the field to settle there.
Exactly. That's the proposed mechanism.
What's quite profound about this idea, if it holds any water, is that the probabilities we observe in quantum mechanics might ultimately be rooted in the quantum dynamics of this underlying field that shapes space-time itself.
It's a deep thought. Probabilities emerging from space-time field dynamics. Yeah. And finally, the source touches upon a truly far-out concept.
Even more far out.
Just a little bit. The idea that the change in energy of the Fichy field as it transitions to a new minimum, let's call it IC-phi,
the energy released or absorbed by a field settling,
could actually be the measurement energy at proper UX that we see in the core DTF formalism.
Connecting the collapse energy to the fundamental DTF energy relation.
Potentially, and even more speculatively. Go on.
This change in the Fichy field might leave a tiny fleeting imprint on the local curvature of spacetime, because phi, like all fields, should couple to gravity.
Whoa, a gravitational signature of quantum measurement.
Talk about a subtle ripple in the fabric of reality. Extremely speculative, of course.
But it connects the seemingly abstract quantum event of measurement right back to the very structure of spacetime, suggesting a potentially deep and perhaps even in principle observable link. Though incredibly difficult to detect, presumably.
Unbelievably difficult, if possible at all. So let us briefly recap this incredible speculative journey we've taken, thanks to your input.
It's been quite a ride.
We've explored how the concepts within differential time flow, particularly this Fichy field's interaction with the intensity of quantum amplitudes, that's A2, might offer a completely new,
though currently theoretical
way to understand why the Born rule works, why it's the square, and why quantum probabilities are always non-negative. And it's vital, absolutely vital, to remember that these are highly imaginative interpretations.
Yes, let's stress that again.
They venture far beyond the well-established frameworks of both quantum mechanics and, frankly, DPF as it's currently understood mathematically. The sources don't provide a rigorous mathematical model to back these specific ideas up.
No, it's conceptual exploration. But what a fantastic aha moment this could be for you, our listener, who brought this fascinating material to us.
Definitely food for thought.
This has been an exercise in connecting some of the most abstract ideas in physics, hasn't it? Offering a tantalizing glimpse into potential future paths for theoretical exploration.
And highlighting the enduring mysteries that still surround the act of quantum measurement.
Absolutely.
Which leaves us with a final, really thought-provoking question, doesn't it?
Go for it.
Could the very fabric of spacetime and its dynamic response to this intensity of quantum possibilities, could that be the key to unlocking the probabilistic nature of reality?
Exactly. Could it be that time itself, at its most fundamental level, is intrinsically intertwined with a multitude of quantum possibilities? It's certainly a lot to contemplate.
Is.
We really encourage you, our listener, to delve deeper into these ideas if they sparked your interest. Perhaps explore more about the foundations of quantum mechanics, the measurement problem itself. Maybe look into dynamical collapse theories, other alternative interpretations.
There's a lot out there.
There is. Share your own thoughts and interpretations. We'd genuinely be interested to hear them.
Absolutely.
And as always, thank you for joining us on this deep dive into such fascinating and, yes, very speculative territory.